In this video, we're going to explain a coordinate-free formula for the exterior derivative. So the previous two videos use coordinates, which is fine, but our manifolds might not have, obviously defined coordinates, and coordinates are some choice that we make, and we don't want necessarily to. We want to know that the objects we're defining are independent of the choice of what coordinates we're using. So to motivate this section, I'm going to first start talking about how to, geometrically, what should sort of d alpha, if alpha is a one form, so d alpha of VW be if alpha is a one form on some Rn, and actually let's just do R2, and V and W are constant vector fields on R2. I'm going to be breaking this video up into two parts. So the second part will talk about what happens when V and W are non-constant. Okay, so what should this be? So d alpha of VW should measure some area of a parallelogram. So in particular, d alpha of VW of WV should equal negative d alpha of VW, because basically I'm just switching the order in which or the sign of the area I'm computing, the order in which I'm looking at the sides of the parallelogram. And it should also somehow measure how alpha is changing with respect to V and W. So we'll first think about how I could possibly cook up something that deals with this second bullet point, and then we'll go back to the first. So if I have a one form alpha, I can plug I can plug V into alpha and get a function. This function, so alpha of V, which is now a function from R2 to R, right? So basically what happens is alpha of V takes a point and evaluates alpha at P and then V at P, and plugs V at P into alpha at P. And now that I have this function, I can take any other vector field W and take the directional derivative of this function, alpha of V, in the direction of W. So this is one way to approach this second bullet point here. So get this function and then take its directional derivative. So we're going to come up with some in coordinates. So right now we haven't talked about any coordinates at all, right? So I'm going to come up with some in coordinates formula for this, and then we'll take into account the first bullet point, write down a formula that makes sense, and then show that it's equal in coordinates to the formula we've derived in the previous two videos for the exterior derivative. Okay, so let's give everything names. Let's say alpha is a1 dx1 plus a2. Actually, maybe let's just call these f and g. It's a little bit easier. F dx1 plus g dy, f dx plus g dy. And v is the vector v1 d by dx1 plus v2 d by dx2, the vector field. And v1 and v2 here are constants. That's very important. So then alpha of v is the function that, so the dx eats v and spits out, so this will be v1 times f plus, and then the dy eats v and will spit out just the v2, so I'll get plus v2 times g. And then when I want to compute the directional derivative of alpha of v in the direction of w, I should be taking d alpha at v and applying it to w. So d alpha at v is v1 df plus v2 dg at W. And here I'll assume that W is equal to W1 d by dx1 plus d by dx plus W2 d by dy. And I think I made a mistake here. That should be a d by dx and d by dy. Okay, so then when I actually write down what df and dg are, this should be v1 df dx plus, v1 df dx plus v2 dg dx times w1 plus, well, let me write out the whole thing. So this will be dx plus the coefficient of dx, and then the coefficient of dy will be v1 df dy plus v2 dg dy, all applied now to w. Applied to w1 d by dx plus w2 d by dy. Whoops. Okay, so then plugging everything in, I'm going to get v1 w1 df dx plus v2 w1 dg dx plus v1 w2 df dy plus v2 w2 dg dy. Okay, and then so this is some sense of what I could do to compute how alpha is changing with respect to v and w. But I could also switch the order of v and w, and I won't get the exact same thing, right? What I want is measure this sort of how alpha is changing, and then get, when I switch the order, the negative of what I got before. So let's, I'll put this in a box. So this is d alpha v in the direction of w. And if I compute the exact same thing, d alpha of w in the direction of v, but with the roles of v and w reversed, I'm going to get v1 w1 df dx plus w2 v1 dg dx plus w1 v2 df dy plus v2 w2 dg dy. And now notice that these are definitely not the same, and they're not negatives of one another. But if I define, so what I'm going to define d alpha at vw to be d alpha at v at w minus d, I guess actually I should be doing this in the opposite order. So this is d alpha at w of v minus d alpha at v of w in the direction w. So what I'm going to do is take the second formula and subtract the first. So when I do that, each of these terms, the 1 term and the 2 term, are going to cancel out. And what I'll end up getting in coordinates is going to be w2 v1 minus v2 w1 dg dx plus w1 v2 minus v1 w2 df dy. And the important thing to see is that now d alpha of wv is the negative of d alpha of vw, because I should just switch every term. So this will be, I mean, I can go through this formula, or I can just go through this formula, which will just immediately tell me that it's negative d alpha of vw. Okay, so this is good because I'm satisfying this first bullet point that I wanted, which required me to measure the area of some parallelogram. And you know, I'm not exactly telling you what that parallelogram is. If you go into your book, there's some nice pictures in terms of the tangent planes, so the functions um, d alpha v and or alpha v and alpha of w. But really, we're just sort of taking this a as inspiration because we know two forms need to be measuring areas of parallelograms, so we know they need to satisfy some property like this, some negativity property. Okay, so this is how I've defined d alpha at a pair VW. And let's use this to get the expression in coordinates that we had before. So what we had before, okay, so